Hello. Okay, so basically, let's review the definition of almost sure convergence. So we have a sequence of random variables, x of n, x1, x2, x3, and so on, going to or converging to a random variable x almost surely, and it's denoted as xn with an arrow, with here almost surely to x, or with probability 1. If, and again, there are like a number of definitions. All of them, are equivalent, and in some problem, one of them will be like more convenient than the other, and conceptually, one of them will be like more like insightful than the others. So basically, for every epsilon greater than 0, for every positive epsilon, there exists an m such that for every n greater than or equal to m, the distance between xn and x is less than epsilon. Okay, so for every m, there exists an m. So somewhere there is an m such that all over here, when m is greater than or equal to m, this distance between xn and x, which is the limit random variable, this is less than epsilon. So to have almost sure convergence, this specific probability must be exactly equal to 1. And using continuity of probability, this can be written in terms of this limit. Or another way of putting it, that basically for every m, there exists an n such that so n is greater than or equal to m, such that you have a violation of the small distance. In other words, that the distance between xn and x exceeds epsilon. So if for every m, there is always some n greater than or equal to m, such that the distance between xn and x exceeds epsilon, it means that xn, if you just try to interpret this statement deterministically, it means that the sequence xn is never converging to x, because for every m, you can always find an n greater than or equal to m, such that this distance grows above some specified threshold, which is epsilon. Okay, and so here is like no, it's basically xn is not going to the limit x, and so probabilistically we want the probability of such event to be exactly equal to 0. And if that is the case, then we say that xn converges almost surely to x. And again, using continuity of probability, this can also be expressed in terms of a limit. We can also write down things like this. And in the previous lecture, we actually proved that there is an equivalence. And in references and so on, you can see that these things are written, formally like this: xn of omega is equal to x of omega. So basically, by the end of the day, the random variable is a measurable function that is defined on a sample space. And so basically, its domain is the sample space, and small omega is an element in the sample space. Here we basically, we sort of we don't think about the sample space and the original definition of the random variable. Okay, it's not needed. It's nice to know, and sometimes it's useful. But like here, we can just do the things like as we do like in engineering and so on. But again, like you can see things like this with an omega and so on. It's really not saying anything new. It's just reminding you of what a random variable actually is. Okay, almost sure convergence again is an important concept, and to like basically grasp it, and you need like to solve many problems, and these problems will lead you like to use one of the forms that we have right here. This is like like anything in math. You just need to practice and practice. Okay, so here is our problem now. So it is life generally has its fraction of ugly encounters. Okay, so here is an ugly encounter. So you are perhaps thinking about something, who knows? but you face this basically stark choice. You have to solve this problem, or whatever. It's scary, but yeah, it's true. Life has many ugly encounters, and you need to be prepared. But let's focus on our business. You need to solve this problem that you have basically a sequence, which is the C sequence. So the C sequence, basically the number C's, they are positive, and they live between 0 and 1. When n is greater than or equal to. So you start from 1, and then every number here is from 0 and 1, and it is monotonically decreasing. Okay, and it actually approaches 0. Okay, so that's it's a deterministic sequence. So the C's are not basically random variables or anything. It's just a deterministic sequence. So our random guys are basically the Y's, and those are independent. Okay, so independent. Perhaps we'll use this in our proof. And then basically Yn is a two-valued random variable. So it can be 0 or it can be equal to Dn. And so what is Dn? So Dn is, basically it's a member of a sequence D1, D2, D3, D4, and so on. And D1 is 1, but now this sequence D1 is non-decreasing. Okay, so basically it remains constant or it increases. Perhaps it basically blows up to infinity. So basically this is Dn here. This is the second value of Yn. So Yn is either 0, and this happens with probability 1 minus Cn. And or it is equal to this Dn with probability Cn. Okay, and so the question is, does this sequence converge? And we want an answer that is, that covers all the possible cases, right? So, the issue with these problems is that they are not specific. So, in the previous lecture, actually, we sort of solved a special case, like, Yn is equal to 0 with probability, let's say, 1 minus 1 over n, and it is equal to n or 1 with probability 1 over n. Now, basically, this is like a very, it's a very, like, sort of large generalization of the problem. And in that case, you must keep in mind that perhaps the answer is not, that you have almost sure convergence, and that there is no almost sure convergence. Perhaps the answer is conditional. Perhaps if something is true, if a set of conditions is true, that then you have convergence, otherwise you don't have convergence. Okay, and so it may, again, and when you find all those unknowns, sequences, that they are not really given, but they are described, just, their general trends. It may feel like you are dealing with a very difficult problem, but it's not. Okay, so let's see what is going on here. First order of business is like to check whether we have convergence in probability, and it will be clear why we do this. Okay, so convergence in probability is like easy to study relative to almost sure convergence. So we take the probability that Yn is greater than epsilon. So you choose any epsilon that is greater than 0, and then you ask yourself, what is the probability that Yn will exceed epsilon? And you take the limit as n goes to infinity. Well, if this limit is 0, then we have convergence in probability. Well, if Yn is greater than epsilon, then the probability is either 0 or it's equal to Dn. Remember that Yn is basically a two-valued random variable, so it's either 0 or equal to Dn. So if you ask whether Yn is greater than a positive number, if the positive number is here, then the probability is 0. If the positive number is there, then the probability that Yn is greater than epsilon is the probability that Yn is equal to Dn. And this probability by the probability statement is equal to Cn. And Cn by the problem statement, it goes to 0. It goes to 0 as n goes to infinity. So this is 0 as required. So Yn converges in probability to 0. Okay, so this may seem like outside what the problem is talking about, but in fact it is very related, because remember this uniqueness theorem. So the uniqueness theorem tells you something that, so suppose that you have convergence in some sense, then in any other sense of convergence, you have no convergence or you have convergence to the exact same limit. So the moral of the story is that if you want to study almost sure convergence, then since Yn as a sequence of random variables converges to zero in probability, then when we study its almost sure convergence, basically we study almost sure convergence to zero. If we do not establish it for zero, then there is no almost sure convergence, right? So because if there is almost sure convergence, it will be to the exact same limit, which is zero. Otherwise, there will be no convergence to zero or to any other limit. Okay, so that's the idea of of starting the problem by basically solving like sort of something that may not like appear to be relevant in the problem statement, but actually it is very relevant because now we know that our candidate limit for almost sure convergence is zero, and now the remaining part of the problem is to decide whether we have almost sure convergence to zero or basically we don't have almost sure convergence to zero, and actually this will be no convergence in the with probability 1. Okay. So basically, we have almost sure convergence if if for every epsilon we have this, so this is just a reiteration of the definition. Okay, so again, like this is one form of almost sure convergence, that for every epsilon greater than zero, as I said above that, so this thing here, I mean, to understand it, so this is like Yn minus zero is greater than epsilon, right? This is the definition of almost sure convergence. Now our stuff here is non-negative, so we can remove the absolute value, and because of this statement here, then we focus on almost sure convergence to zero. And so we can just write things as the probability that for every m there exists an n greater than or equal to m such that Yn exceeds epsilon. So we want this probability, which is the probability that Yn exceeds epsilon infinitely often, we want this to be zero. Because because this event is like the event that there is actually no convergence. So we want this probability to be zero. Okay. Now, what is the sum of the probability that Yn is greater than epsilon? So again, as I said when we studied convergence in probability, that this probability is hour bounded by the probability that Yn is equal to Dn, which by the problem statement is equal to Cn. And this sum, what about this sum? Well, the problem statement is silent. It just tells you that the sequence Cn, it goes to zero. But if the sequence Cn goes to zero, we cannot tell whether this series converges or not, right? So if the nth term converges to zero, perhaps also we have divergence. So in that case, we need actually to impose this condition. Okay, so our solution should be conditional. So if this summation is finite number, then if this summation is a finite number, so basically the sum of those probabilities, so this is the event that Yn exceeds epsilon, if you want to be like to stick to the very letter of the definition of almost sure convergence, if you want basically this event here, if the sum of the probabilities is finite, so this sum is hour bounded by the sum of the c's, and if this sum is finite, then by Borel-Cantelli lemma 1, right, basically the probability infinitely often of this event will be exactly equal to zero, which means that we have almost sure convergence. Okay, now if the sum, the probability that Yn is greater than epsilon, now if you take the value that epsilon is less than 1, so if epsilon is less than 1, it means that always, remember that the sequence Dn is always greater than or equal to 1. So if epsilon is less than 1, it means that epsilon is less than Dn. Then for those epsilons, then this summation, this summation with Yn greater than epsilon will be that Yn is equal to Dn with equality, and as I said, this will be the summation of Cn. Now, by Borel-Cantelli lemma 2, if this summation diverges, and note that the guys are independent. Remember, in Borel-Cantelli lemma 2, you need you need basically the here y2 and so on. You need them to be independent, and that is here in the problem statement. So if the summation is plus infinity and because we have independence, then we can apply Poral-Cantelli lemma 2, and in that case, this probability that yn exceeds epsilon infinitely often is equal to 1. Remember that we want this probability to be equal to 0 for almost sure convergence. Now, actually, it is not 0. It is actually 1, and so we have no almost sure convergence to 0, and actually we have no almost sure convergence. So the answer to the question is basically conditional. It depends on basically the sum of Cn as n goes from 1 to infinity. If this sum diverges, we have almost sure convergence. Otherwise, we don't have almost sure convergence. Now, sometimes people find it like sort of difficult to fit the statement of an almost sure convergence problem to the Poral-Cantelli lemma, despite the fact that they are very closely related. Again, it's like if you go upstairs here to the main definition of almost sure convergence, one of the definitions is basically this. It's a study that the probability that xn minus x greater than epsilon infinity often. We want this probability to be 0. And the infinity often business is that of Poral-Cantelli lemma. So Poral-Cantelli lemma is used a lot in basically in proofs for almost sure convergence. Okay, but suppose that it escapes you. Somehow you find it difficult basically to match an almost sure convergence problem to the Poral-Cantelli lemma. No problem. Do things without referring to the Poral-Cantelli lemma. What will happen, by the way, is that you will find yourself like sort of repeating the proofs of the Poral-Cantelli lemmas 1 and 2. Okay, so exactly this is how you do it. So suppose you start with this thing, with this probability that the union of n greater than or equal to m yn minus 0 greater than epsilon, it is equal to this summation. It is equal to this summation here. Now, you need for almost sure convergence, you need what? You need to take the limit as m goes to 0. So you need to take the limit. So basically, what is this limit? Limit m goes to infinity of summation m infinity cn. Okay. We know this. If the sum starting from 1 to infinity, if this sum converges, then if you start from m and then take the limit as m goes to infinity, then this summation will basically go to the limit actually will be 0, right? So it's the same thing. So if this is if this sequence I should actually write it like if this summation n from 1 to infinity Cn is less than infinity, then the limit as you start from m and you take the limit as m goes to infinity will be 0. And if it's 0, then according to one of the definitions of almost sure convergence, we have almost sure convergence. So basically, what you are doing here is union bound. Okay, so you are applying the union bound by saying that this probability, which is in the definition of almost sure convergence, is upper bounded by the sum. And guess what? If you go and review the proof of Poral-Cantelli lemma 1, basically it is a one line and it uses the union bound. Okay. So again, if it escapes you, you basically have to match the problem to the Poral-Cantelli lemma. I mean, you can use standard things like union bound, and you will also get the result that you have almost sure convergence. But basically, you need this guy to be to go to 0 as m goes to infinity, which requires that the summation starting from any finite number should be equal to a finite value. Now, if the sum diverges, then you have an upper bound that is infinity, which tells you nothing, right? If you upper bound the probability by infinity, well, I mean, it's basically telling, well, any probability is less than or equal to 1, so it's less than or equal to infinity. So there is nothing to be gained here. So we need like to basically study the second scenario in which the sum of the C's is basically is divergent. Then we need like sort of to restart our proof. So in the first case you do the union bound, but then you say, well, let's use this probability here, the probability that, the intersection n from greater than or equal to m of y n minus 0 less than epsilon. Now remember this thing, to show almost sure convergence, you need to take the limit as n goes to infinity and show that the limit is equal to 1. Now this is the probability of an intersection, and because we have independence, then the probability of the intersection is the product, and the probability that yn is equal to 0 is 1 minus cn, and then we have our very nice inequality. Again, it was used in the proof of Borel-Cantelli lemma 2, 1 minus alpha is less than or equal to e to the minus alpha. So this product here is upper bounded by exponential minus summation n greater than or equal to m of cn. Now, if basically this summation, if the summation Cn n from 1 to infinity diverges, then basically if you start the sum at any index, then it's also infinity, right? And we did we said an argument for this before. So if this if this summation is infinity, then this starting from any m of your choice will also be infinity, and exponential minus infinity is 0, and so you have a probability that is less than or equal to 0. Then the probability is 0, and if you take the limit as m goes to infinity, then it is also 0. So in that case, this probability goes to 0. But to have almost sure convergence, we should have it go to 1. So we don't have almost sure convergence. Okay. So basically, the idea is that our answer to this problem is conditional, and it depends on whether the summation n from 1 to infinity of Cn, whether it's basically a finite number or basically infinite. Okay. Any questions? So actually, last time we stopped at this, the strong law of large numbers. So this is a version for independent but non-identically distributed random variables. So the x's are 0 mean, independent. Each one has its own variance, and then we have this, this summation here, this condition here, which is like if you take the variance of xi and divide it by I squared, and then you sum over the natural numbers, then you get a finite number. Okay. Then if this is the case, then the sample average, okay, so this quantity here is 1 over k summation I from 1 to k xi. So this, so the sum over the number of the terms, then it will converge almost surely to 0. Okay, but we need this term here. Okay, and the idea is that we will use the HR inequality that you studied in the tutorial session. Quickly, basically in the tutorial session, you took basically this form that you have this probability k. So basically k here goes from m to n, and it is upper bounded by things that are related basically to the sequence c, and c is a sequence that is non-increasing. It's a positive sequence that is non-increasing, and it depends on the variances. Now, it's easy to show that you can make n go to infinity. Okay, so this probability is exactly equal to this probability, right? So when you say that the probability that the maximum k from m to n of ck sk, so sk is the sum of those 0 mean independent random variables greater than epsilon. This is exactly equal to the probability that k greater than or equal to m, and here it stops at n of ck sk magnitude or absolute value sk is greater than epsilon, right? So basically, if the maximum exceeds epsilon, then one of the guys exceeds epsilon, right? And if one of the guys exceeds epsilon, it must be the case that the maximum exceeds epsilon. So basically, these two events are equivalent. Okay, so this maximum and the union. So you can write it as maximum, you can write it as union. It's exactly the same, right? So we write it as a union, and the idea of writing it as a union, which is different from what we have seen in the tutorial session, is basically that writing it in union will let you see that we can apply, we can take the limit as n goes to infinity, and then apply directly the law, of continuity of probability. So by continuity of probability, so when you take the limit as n goes to infinity, by continuity of probability, you can basically have basically this union k greater than or equal to m going to infinity. And on the other side, when you take the limit, by the definition of an infinite sum, if you take the limit as n goes to infinity, then this is actually the definition of having an infinite sum, right? So the infinite sum, it means that you sum to some large number, and then you make it larger and larger by taking the limit. That's actually the definition of, or one of the definitions of infinite sum. Okay, so I'm not like basically cheating here. The inequality is also valid if you take n goes to infinity. Okay, so this is the inequality. The inequality gives you an upper bound, on this probability here. And again, don't forget that this probability can be written in terms of the union, which is also what we have seen in the definition of almost sure convergence. Okay. Now, so actually, let me put it like explicitly. So this is the probability, k greater than or equal to m, 1 over k absolute as k greater than epsilon. So we want, if there is almost sure convergence, we want the limit as n goes to infinity of this thing to be 0. Okay, so we want the limit as n goes to infinity to be 0 to basically have almost sure convergence. What we have is an upper bound on this. So by the sandwich theorem, this is a non-negative quantity, and so we just need to take this upper bound and show that actually it goes to 0 as n goes to infinity. If we do so, then we are okay, and then there will be almost sure convergence. Okay, so we have two terms. So basically, the right hand side, it has two terms. Okay, so this is the first one of them. And it is a summation in which, like, you take the variance divided by k squared. So basically, this is the here what I am using. I am using the HR inequality with this constant. Those guys. I'm taking ck to be equal to 1 over k, which is a special case. Okay, which is fine. I mean, basically, you prove that basically this inequality is true for any positive sequence that satisfies this property. Then 1 over k is one of those sequences in which, so it is a positive. Ck is always positive, and it is non-increasing. So again, go back here. So we want this guy to go to 0. I mean, if we want almost sure convergence, we want basically this guy to go to 0. Well, if you start your summation from 1 to infinity, and this summation is finite. Then now if you start from n plus 1 and take the limit as n goes to infinity, then it will be 0. Okay, so now you understand why actually we have this apparently weird condition. Okay, so this condition right here is that, I mean, so you want almost sure convergence. You want to have at least a sufficient condition that will that will make you like basically sure that you have convergence with probability 1. Then you need this condition, because if you assume that this is true, then if you start your summation from some number and then n and then take the limit as n goes to infinity, then this will be 0. Okay, so now you see basically why this weird condition is in the statement of the theorem. Okay, it allows you to say, oh, this goes to 0. But we are not done, because we have the sum of two non-negative quantities, and we want also to show that that basically this term here, also when n goes to infinity, that it will go to 0, and then the probability, which is non-negative, is upper bounded by something that goes to 0 as n goes to infinity. So the limit of the probability itself is 0, and we have almost sure convergence. So our friend here will be actually Kroneker's lemma. Again, part of your tutorial session, and the nice thing is that we, the Kroneker lemma, again, a special case that is also depends on this form here. So the Kroneker lemma, this is the special case that is needed in this proof. If this summation is finite, then basically you can't, then if you have a summation from 1 to m, and then you sum the variances only, and you divide outside the sum by 1 over m squared, this limit will be equal to 0. So that's basically the Kroneker's lemma. Okay, the version that actually is, so in the Kroneker's lemma, if you go to its definition, it has like two sequences, and one sequence here is k squared, and the other is sigma k squared. Okay, so it tells you that if this is true, so again, this is another justification of having this condition in the problem statement. If this is true, Okay, so summation k from 1 to infinity 1 over k squared sigma k squared is less than infinity. So the Kronecker lemma tells you something very nice. It tells you, you know, if you now sum k from 1 to m, and you sum sigma k squared, okay, so you don't have 1 over k squared inside some k, but outside you have 1 over m squared, then if you take the limit as m goes to infinity of this quantity, it will be equal to 0. Okay, so using the Kronecker lemma will actually tell you that also this other guy will go to 0. So both guys here will need this funny condition, and so if you have a problem and you want to apply to it the Kolmogorov strong law of large numbers, then you need to check it. So okay, so you need to check basically this thing here, as we will see towards the end of this lecture. So you need to, you don't have like to prove anything from scratch. I mean, the theorem is already there, but you need to set, you know, basically to check. You need to check that basically the conditions are satisfied, and then you can enjoy the theorem. Okay, so so basically this is the main condition to be checked, that you want the sum of variances divided by, you know, I squared. It should be a finite number. If it's a finite number, then you can apply basically this theorem here. Okay, and this theorem will be used later to prove the strong law of large numbers for IID random variables. For IID random variables, we don't need a strong condition like this. Okay, we will need just one tiny condition, which is that the first moment is finite. So the strong law of large numbers, you know, when I just say strong law of large numbers, I mean the IID case, and it is a generalization of the weak law of large numbers, but rather than having convergence in probability, it will be convergence almost surely. Okay, and basically the nice thing is that and actually it is the challenge, is that, you know, you don't need any assumption regarding your random variables, you know, so, you know, you want them to be independent and identically distributed. You want the first moment to be finite. But if you look here, you know, for this case, if they are not identically distributed, you need each variance to be finite, of course, and then you need more. You need basically summation I from 1 to infinity of sigma I squared over I squared to be finite. For the IID case, you can let go of all these things that are related to the second, you know, the second order statistics or the variances, and you can just, you know, you need to just verify that your random variables have a finite first moment. Okay. However, it is the, you know, one way of proving the strong law of large numbers is actually to use, you know, the Kolmogorov strong law of large numbers, as we'll see. Okay. Any question? This is like a summary of the relationship, you know, between the various modes of convergence for random variables. So we have convergence in the Rth mean. You know, it allows automatically that, you know, if you choose an S between 1 and R, then you also have convergence in the S mean. And the convergence in the S mean will mean convergence in probability, and convergence in probability implies convergence in distribution, and almost true convergence implies convergence in probability. Now, you know, if there is no implication arrow in this diagram, then it means that generally speaking, there is no relation. However, there are relations like in special cases. So one example, like in the previous lecture, we said that basically we have this. Okay, we have this if convergence in distribution to a constant or a degenerate random variable. So convergence in distribution to a constant actually implies convergence in probability. Now you will do a problem in the homework that basically convergence in probability means that there is almost true convergence for a subsequence. Okay, so there exists a subsequence converging almost surely. And also in the homework, you will show that basically if you have convergence, you know, if your sequence is asymptotically bounded or is eventually bounded, then also convergence in probability will, at least in the problem, you will show that it will imply convergence in the mean square. Okay, so so sometimes we have basically partial converses. Okay, so but those are all, you know, under some conditions. but the diagram without those green implication arrows, those are always guaranteed, and you can just use them directly in in solving problems. There are like results we will take without proofs that are so useful, and again, just make use of them. For example, there is a continuous mapping theorem which tells you that for almost true convergence and convergence in probability and convergence in distribution. Note that we don't have convergence in the Rth mean or mean square convergence. Okay, so you need to basically pay attention to these things. So if you have almost true convergence or convergence in probability or convergence in distribution of a certain sequence of random variables, then applying a continuous function to both sides is okay. So for example, if Xn converges almost surely to X, then G of Xn, where G is a continuous function, you must check that it is indeed a continuous function, it converges almost surely to G of X. Same applies if you have convergence in probability or convergence in distribution. Now, what about the limit arithmetics? So when you take a course in calculus, then the first chapter is typically about limits, and once you study limits, the epsilon delta definition, then you start like talking about what is the limit of a sum, what is the limit of a product, what is the limit of a quotient, and so on and so forth. So it turns out that many of those properties are preserved in convergence of sequences of random variables, which is nice. So if Xn converges almost surely to X, Yn converges almost surely to Y, then the sum converges to the sum and the product converges to the product. Cool. And actually, we did the proof of this thing in the previous lecture. Basically, the same story is applicable if we have convergence in probability. Okay, cool. Now, if you have convergence in the Rth mean, then the statement is true if we are talking about the convergence of the sum, not the product. The sum, not the product. Okay, so Xn plus Yn converges in the Rth mean to X plus Y. Product, you cannot tell. You need to check. Okay, so again, it's not the conventional limit arithmetics are not applicable like general for all cases. Okay, so here if you have convergence in the Rth mean of X of n and Y of n, sequences X of n and Y of n, well, regarding the product, perhaps X and Yn is not converging in the Rth mean to XY. Okay, but for the sum it is guaranteed. Now, what if you have convergence in distribution? Then the following statements are called Slutsky's theorem, and well, they tell you that you have what you like to have. Basically that the sum converges to the sum and the product converges to the product. But there is one condition. The condition is that one of the sequences, so right, we have two sequences converging in distribution. One of them must be converging to a constant. If both sequences are converging to non-degenerate random variables, then basically these statements are generally not true. Okay, so again, for convergence, like almost true convergence, I mean, you don't need to check anything. If this is true and that is true, then the sum converges to the sum and the product converges to the product. Same for convergence in probability. What about convergence in distribution? It is okay, but you need to check one thing, that at least one of the two sequences, here I'm taking sequence Y, it must be convergence in distribution to a constant. Otherwise, we are not sure, basically, whether the results hold or not. So, if Xn converges in distribution to X, Yn converges in distribution to a degenerate random variable, then the sum converges to the sum and the product converges to the product. Okay. Now, the theorems that I talked about, the continuous mapping theorem and things like Slotsky and the limit arithmetics and so on, they will allow you actually to combine with the weak law of large numbers and the strong law of large numbers and so on, and the central limit theorem. All these things can be combined together to allow you to solve apparently very complicated convergence problems. Okay, so you can make use of those theorems to basically to crack problems that may look like very difficult to handle using the main definitions of convergence. Okay, so that's an example. Suppose that the sequence Xn converges in distribution to a Gaussian random variable, a standard Gaussian. Yn is a sequence of positive IID random variables with a finite first moment. And what you are needed to do is to study the convergence of nx of n divided by the summation of k from 1 to nyk in distribution. Okay, so you know, I said last time, you know, convergence in distribution, like the main definition is with CDF, but it is like typically using the CDF will lead nowhere. So we have basically the characteristic function, and the characteristic function is so nice. Like if you are dealing with things like a sum of independent random variables. But here the situation is even more complicated because basically we have a sum of the y's, and the sum is in the denominator. Right, so if you take the characteristic function of this thing, who knows what it is? Okay, so and actually we don't even know the distribution of the y's. Yn is a sequence of positive IID random variables with a finite first moment, and that's it. Okay, so we don't even know the distribution. Okay, and so you know, so here, this is one of the situations in which basically, you know, the way to go is not to use the main definitions of convergence, and the way to go is not even like, because it's convergence in distribution, it's not to use the characteristic function, but basically to combine, you know, the theorems that we, you know, that we have investigated here, and, you know, 1, 2, 3, and you'll find yourself being able to make statements regarding seemingly complicated quantities like this. So let's see exactly what I mean. Now, you have a sum here. You have a sum. Okay, you have a sum. And, you know, so basically we have, you know, the sum you can basically, you know, scale it by 1 over square root n or 1 over n. And we have theorems regarding this. Yn is a sum with a finite first moment. Okay, so finite first moment and an IID sequence. Okay, so, you know, some part of your brain, you know, some part should like law of large numbers. Something should, from inside, should tell you law of large numbers. Okay, because you have finite first moment. Okay, so something like the central limit theorem will require that you have a finite second moment. But here it is finite first moment, and you have a sum, then law of large numbers. Okay, and since here we are studying convergence in distribution, we do not really need like the strong law of large numbers. We can just go for the weak law of large numbers. So by the weak law of large numbers, basically this quantity, because the y's have a finite first moment, it converges in probability to the first, you know, to the first moment, which is a finite number. And because those guys are strictly positive random variables, then the first moment will be strictly positive. Okay, so you know, but you look here and you look there. I mean, yeah, I mean, come on. I mean, basically, this is fundamentally different from that. But now, you know, you start basically using our results in succession to tackle this quantity. So first, I mean, the problem is about convergence in distribution. The weak law of large numbers is a statement about convergence in probability. Well, we know that convergence in probability implies convergence in distribution, so you can basically replace this by that. Okay. Then we have this guy in the denominator. Well, the function 1 over alpha is continuous on R plus. And so now you can apply the continuous mapping theorem and say that basically if this thing converges and, you know, this guy is not equal to 0, then 1 over n summation k from 1 to nyk, that this thing converges in distribution to 1 over the expectation of y1. So this is by the continuous mapping theorem. Okay, so yes, I mean, this is a valid statement. Now the challenge is that we have basically this, you know, this x of n in the numerator. So basically this, you know, the 1 over n that we needed so that we can use the weak law of large numbers is basically this n here. Okay, and so the idea is that we took this quantity and thought of it as x of n as over 1 over n summation k from 1 to nyk. So now again, using the weak law of large numbers, this quantity here in the denominator is going to the expected value of y, and then by the continuous mapping theorem, then 1 over this will go to 1 over the expected value of y1. It's, basically this sequence is IID. Now we have a product, right? So you can think of this as a product. We have a sequence Xn, and according to the problem statement, this sequence is converging to a standard Gaussian, and then this is multiplied by 1 over n summation k from 1 to ny k, and now we know that this sequence will go to a constant. So that's basically Slotsky. So Slotsky tells you that, if one sequence converges in distribution and the other sequence is converging in distribution to a degenerate random variable, then the product will converge to the product. Okay, so by Slotsky, then, this quantity here, which again, if you want like to use Slotsky, again, you can write it as x of n multiplied by 1 over n summation k from 1 to nyk, then basically it converges in distribution to the product. Okay, and so basically this guy, it goes to the standard Gaussian, and this guy goes to this constant that is right here, and basically standard Gaussian scaled by constant, it is a Gaussian whose variance is basically the square the square of this quantity that is right here. So this quantity here, again, the seemingly complicated quantity, now you can study its convergence in distribution, and it will converge to a zero-mean Gaussian random variable with a variance that's equal to 1 over basically the square of the first moment of basically y1. So again, so here, this is the power of these theorems. You can basically combine them to prove problems, and I think there is another exercise, okay? Okay, but before I move, any question? So now we have a bit more, it's apparently complicated, but these problems, once you get used to them, they are basically guaranteed. You have the x's, zero mean, IID random variables, finite second moment. Okay, so perhaps there is like central limit theorem, or perhaps still we will use the law of large numbers. We will see. Investigate the convergence in distribution. Now we have a sum. So now we have, basically the same family of random variables, which is the x's, but we have a numerator, and this numerator involves the sum of the x's themselves, and we have a denominator, and this denominator involves the sum of the squares. So the squares are basically other random variables. So so you can think of the denominator here, k of 1 to n x of k squared. If you attach 1 over n, this is like summation k from 1 to n yk. Okay, so you can think that yk is equal to xk squared. Now, since the x's, they have a finite second moment, then those y's, they have a finite first moment, because the first moment of y is basically a second moment for x, and this, by the problem statement, this is the finite number. Okay, so we can actually play the same game of the previous slide, and we can apply the weak law of large numbers to the denominator. Okay, so here is the way to go. You have a sum here, you have a sum there, you have this square root n thing. You can split this square root n thing and write it as 1 over square root n, and 1 over n, 1 over n. So 1 over square root n, this is basically the scaling factor when we do the business of central limit theorem, and 1 over n when we do the law of large numbers. In the denominator, by the weak law of large numbers, we have convergence to basically the second moment here, which, because the guys are zero mean, then it is equal to the variance. And as in the previous example, then you can apply continuous mapping theorem. The reciprocal of this guy will go to the reciprocal of that guy, and convergence in probability implies convergence in distribution. Now, what about the numerator? So in the previous example, basically the numerator was given explicitly in the problem statement, that it converges to standard Gaussian. Now, we don't have this, but we can apply actually the central limit theorem here. We have those x's are zero mean, they have a finite second moment or a finite variance, and we have this scaling factor, which is 1 over square root n. Then by the central limit theorem, then basically we have convergence to zero mean Gaussian with a variance sigma squared. Okay, and then you apply Slutsky, right? So Slutsky will tell you that basically, again, you can think of this as the product as the product k1 xk multiplied by 1 over n summation k from 1 to n xk squared. So this guy will again, by the law of large numbers, this will converge to a positive constant, and this guy will converge to a Gaussian distribution. So the product will converge to a Gaussian random variable, which is this one. Okay, so again, you can solve again a quantity like this, no way you can deal with this quantity like using the characteristic function or any other thing. Okay, so so this is basically the quantity, and it converges again in distribution to this. And like here is like a numerical simulation, like to have a feeling of those convergence things. So I will take the x's. So they are zero mean IID random variables with a finite second moment. So I choose the x actually to be, the x's to be discrete random variable that take the values minus 1.5, minus 0.5, 0.5, 1.5, each with probability 1 over 4. So yes, zero mean, and the variance is a finite. The variance is a finite number. Okay. So what will happen if you basically if you do this? What will happen if you generate a number of those random variables, and basically you compute this quantity of interest in the problem statement, which is square root n multiplied by the sum divided by the sum of the squares. In that case, so our theoretical investigation told us that we will converge to a Gaussian with this specific variance 1 over sigma squared. And yes, I mean, so this, what we got, the limit is this curve here that, that it's the CDF of the limit, which is the Gaussian with zero mean and the variance 1 over sigma squared. And empirically, this is basically the empirical CDF. So if you take your data, you will find that really your data is approaching the CDF of your data as n gets large and large. Here it's just for n equals 10. So and again, you know this from previous life, that basically that when we say that the limit n goes to infinity, so it means that for large n, how large is large? Sometimes actually you need n to be very, very large so that you see convergence. But like in this example, like if n is 10, then the CDF of the data, when you compute this quantity, the square root of the sum over the sum, it's very close to basically to the CDF of this guy here. And if you even increase n to 1,000, like basically the two curves coincide. Okay, so this is like, so to show you that convergence, and if the convergence here means that if you generate basically random values that are zero, satisfying the conditions of the problem, if you compute this quantity as n gets large and large, basically yes, the CDF of this thing will converge to the CDF of this random variable. And here again, this is an illustration that convergence actually, sometimes, the large n is not really large. Just a relatively small n will give you a close result. Okay. So now we need to talk about the strong law of large numbers, the IID case, which is this statement that we have guys that are IID. Okay, and those guys basically they have a finite first moment, nothing else. Okay, so remember the Kolmogorov strong law of large numbers. You need the variance, each variance to be finite, and then you need basically this this thing here, summation sigma I squared over I squared. I is a natural number, that this should be finite. So we have like basically stuff related to the second order statistics. Here we just need one thing. We need the first moment to be finite, to be a finite number, and in that case, yes, we have 1 over n summation k from 1 to n xk. It will converge almost surely to this first moment. Okay, so in some sense, this is the statement. It looks very similar to the weak law of large numbers. The issue now is that we are proving convergence in a stronger sense, which is the almost sure sense, and hence the name strong law of large numbers. So as a reminder, the weak law of large numbers was proved. So it is a statement about convergence in probability, but it is actually difficult to do it using the direct definition of convergence in probability. And so the plan of attack was basically to show, because basically we suspect that convergence will be to the first moment, which is a constant, or like you can think of it as a degenerate random variable. So the plan of attack was to show a convergence in distribution using the characteristic function, and then convergence in distribution to a degenerate random variable implies convergence in probability. So that was the weak law of large numbers. Now we are basically aiming high, and we want to show that there is convergence with probability 1. So what is the game plan here? What is the strategy to basically do such a proof and forget about using the definition? The definition will lead you nowhere because we have such monster quantity. It's a quantity that basically involves the sum, and basically showing convergence via the characteristic function will not help because yes, convergence basically using the characteristic functions is a demonstration that we have convergence in distribution, which if it happens to a constant, it's convergence in probability. But remember that basically convergence in probability does not necessarily imply that there is convergence almost surely. So basically we need something else, and here is the plan. So first we will basically deal with the zero mean version of the x's. So we will define what UK is xk minus its first moment. So the UKs are, so this is like sort of trivial. This is just a tiny modification. You take the random variables, from each one of them you subtract the first moment, which means that now you have a sequence, the sequence U1, U2, U3, and this sequence is a zero mean sequence. But here is the tricky part. I mean, so this is like, it's not the sort of thing that will come directly to your mind, unless you have experienced it before, right? So it is not something that, again, that is so straightforward. You will define another sequence of random variables, which is the y's. Yk is equal to uk, and then an indicator with the magnitude of uk less than or equal to k. Okay, so what we'll do here again is something. So uk is equal to xk minus the first moment. Okay, easy. But yk is equal to uk, and then it's sort of a truncated random variable. Basically, it is equal to yk, but over a range, so long as the magnitude of uk is less than or equal to k. Okay, so this k here is that k, which means that if the magnitude of uk exceeds k, then yk is equal to 0. Now, because the x's are independent, then the u's are independent, and because the u's are independent, the y's are independent. But now the y's are not identically distributed, because in their definition, basically you use this k here, which means that y of 100 is equal to u100, and basically the magnitude of u100 less than or equal to 100 by y of 213 is equal to u213, and indicator the magnitude of 213 is less than 213, right? So you are using a different number here. So the u's are identically distributed, the y's are not identically distributed. Okay, so it's a gamble. We are gambling here. So basically, somehow we are trying our luck. Perhaps we believe that investigating the convergence of the y's is like sort of easy using the Kolmogorov strong law of large numbers, and then somehow using the convergence, almost sure convergence of the y's, we will establish the same statement for the u's and for the x's. Okay, so will this trick work. Okay, so the idea is, again, we will construct a sequence of independent random variables, but they are non-identically distributed. And they will basically have this indicator, they will have this indicator function. They are not identically distributed because the indicator function will depend, so basically this is less than or equal to 7 if we are talking about y7, but here we have a million if we are talking about y million. We will try to show that basically that the sequence yk from which the first moment is subtracted, that this sequence actually is a sequence for which we can apply the Kolmogorov strong law of large, strong law of large numbers. Okay, so we will try to show this. And remember that for this to be true, remember there was a condition, and of course we need to verify that condition. It's part of the business. Now we will also try to show that basically this deterministic sequence goes to 0, and basically if we have this statement and that statement, we will use both to show that the summation k from 1 to n of yk divided by n converges almost surely to 0. Now, this will be like, okay, we don't care about the y's. They are basically a construction. So the remaining part will be to make this statement about the y's. Basically, we should be able to transfer it. We should be able to transfer it to the u's and hence to the x's, as we will see. Okay, so this is the game plan. And again, it involves basically, this trick of those random variables. They are basically the bridge so that we can prove the strong law of large numbers. And we will use the other version, the version in which the random variables are non-identically distributed. And remember that for that other version to prove it, we needed something like the HR inequality. So see, you have like pieces of the puzzle coming together, and now let's basically carry out this steps. And so we will basically define the u's, the x's minus the first moment, and we will define the y's, and we want to take each y, subtract its first moment. So now the y's, each y minus its first moment will be like a sequence of random variables that are zero mean. The random variables are independent, but they are not identically distributed. And to show that this quantity converges almost surely to 0, we will need to do this check here. Okay, so any question before I proceed? Okay, so the idea is basically to show that something is finite. We do not really need to basically to get its exact value. If we upper bound it by something and the upper bound is finite, then the quantity of interest is indeed finite. Okay, so that's basically the way to go. So what we'll do is that we will take this summation, and we will upper bound this variance here by the second moment. Okay, so the variance is the second moment minus the square of the first moment, and so the variance is upper bounded by the second moment. And then we will replace yi squared by its definition. And so remember that so this is the definition of the y. So basically yi squared is ui squared, and the square of the indicator function is itself. It's a 0, 1 function, and so basically 0 squared is 0, 1 squared is 1, and so this becomes u squared indicator, the magnitude of ui less than or equal to I. For the u's, basically they are identically distributed. right? Because like the x's, they are just like the x's with the first moment subtracted. And so in terms of expectation and probability, basically I can just replace ui by u1. So again, exploiting the fact that the u's are identically distributed. Okay, and so we have this expectation of u1 squared, and then indicator magnitude u1 less than or equal to I divided by I squared. Again, this quantity is not an arbitrary quantity. It is basically what we need to check so that we apply the Kolmogorov strong law of large numbers. So then what we do next is that, and this is something like a proof of, it was a homework problem that I sent you its solution. Like, so the trick here is to take the range of values from 0 to I. So here we have an indicator, from magnitude u1 is a non-negative random variable or a non-negative quantity, and then the magnitude is from 0 to I. And so what we will do is that we will basically split this range. Okay, so we will have an index j from 1 to I, and we will split this range, okay, from, j minus 1. So we'll take from 0 to I, and then we'll take from 0 to 1, from 1 to 2, from 2 to 3, and so on and so forth. So we'll take j from 1 to I, okay, and then this indicator here less than or equal to I will take it, the absolute value of u1 from j minus 1 to j. So when j1 when j is 1, this is from 0 to 1. When j is 2, this is from 1 to 2. When j is 3, this is from 2 to 3. And when j is I, this is from I minus 1 to I. Okay, so we will take this guy and do this splitting. Now we will do our, our second upper bounding. So the first upper bounding is, yes, I mean, we need to talk about the variance, but, basically we will use the second moment. For the second, we will basically take this quantity. So this quantity is u1 squared, indicator j minus 1 and magnitude u1 j. So basically the indicator, it requires that you are basically less than or equal to j. Okay, and so this is less than or equal to, you can replace, so this is magnitude u1 squared, and magnitude u1 by the indicator is less than or equal to j, so this is less than j squared, indicator j minus 1 u1 less than or equal to j. And you can check this, right? So basically, if the indicator is 0, then we have the inequality 0 less than or equal to 0, which is a valid inequality. If the indicator is 1, we indeed have u1 squared less than j squared. Okay, and so we have this upper bounding step with the advantage that now inside the expectation we have two things that depend on u1. We have this u1 squared and we have this indicator, but now this will be upper bounded by j squared, and so we can take it outside and we have an expectation of an indicator which is a probability. Okay, then basically we have basically the summand. So the summand is non-negative. Okay, and so by Tonelli's theorem, we can do the summation in any order of our choice. So we can sum with respect to I first or with respect to j first, right? And so basically, it is tempting here to start by the I because the j is a bit like annoying. So we have j squared and then we have the probability depending on j, but we have here I alone. Okay, so again, like this will give you, like if you are basically doing the proof yourself, at this step you will say, okay, perhaps it is a good idea to start basically by doing the summation with respect to I. Okay, and so originally we have I so I is 1, 2, 3, 4, 5, 6, and so on. What about J? J is from 1 to I. Remember that J was introduced so that we split the range from 0 to I into basically intervals of length 1. And so that, and on each interval, we will upper bound magnitude U1 by J, okay, which, right? So this was basically the idea. Now, J is from 1 to I, so when I is 1, J is 1. When I is 2, J is 1 or 2. When I is 3, J is 1 or 2 or 3, and so on and so on. So basically, this is the grid basically of the double sum. Now we can basically sum over this grid of ij values by taking j to be the outer sum, and now taking j to be from 1 to infinity. Now if you fix a j, so if you fix a j, what will be I? So if you fix a j, like here, I will start from, so I basically will I starts from j to infinity. So basically, if we interchange the order, we will have a summation with respect, j going from 1 to infinity, and I now going from j to infinity. Now there are like several ways of upper bounding, here, and it turns out like to make life you may be tempted like to say that let's upper bound this guy here by pi squared over 6 or something, but it's nice actually to eliminate this j squared and converting into j. So basically the trick that will work here is again a nice trick. You take 1 over I squared and you split it into 1 over I, and then 1 over I is less than or equal to 2 over I plus 1 for every I greater than or equal to. You can check easily that 1 over I is always upper bounded by 2 over I plus 1. Definitely 1 over I is greater than 1 over I plus 1. But 1 over I is less than or equal to 2I plus 1, because this is equivalent to I plus 1 less than or equal to 2I, which is I greater than or equal to 1. Okay, and so what you do here is basically that you upper bound 1 over I squared by 2 over I plus 1, and then this thing here, as you know from doing telescopic sums, that this is 1 over I minus 1 over I plus 1. And again, this is telescopic sum that will give you a summation equal to the first term, which is 2 over j. Now we have an upper bound, and this upper bound now. So again, the nice thing is that this j will reduce this j squared into a j, and we have this probability here. We can basically isolate the term corresponding to j equals 1. So this will give 2 the probability, that the magnitude of u1 is from 0 to 1, and then we have the other terms, and for the other terms we will do another upper bounding. So we will say that j is less than or equal to 2 multiplied by j minus 1, and you can verify that this is true for j greater than or equal to 2. The idea here, why basically changing this j to j minus 1, because if we change this to j minus 1, and if we rewrite this probability as the expectation of the indicator, j minus 1 less than magnitude of u1 less than or equal to j, then basically this j minus 1 is upper bounded by the magnitude of u1. Okay, and so you can basically take this j minus 1 and put it as u1. It's sort of the opposite steps to what we did initially. Okay, so here again what you will do is that you say, okay, you say that j is less than or equal to 2j minus 1. Okay, and so j minus 1 multiplied by this indicator is less than or equal to, so again the idea is that j minus 1 indicator, j minus 1 less than or equal to magnitude u1 less than or equal to j, that this is less than or equal to magnitude u1 indicator j minus 1 magnitude u1 is less than j. Can you check? Yes. if the indicator is 0, you have 0 less than or equal to 0, which is always valid. And if the indicator is 1, then basically you have the magnitude of u1 greater than j minus 1. So that's basically this step here is to have a j minus 1 rather than j, so that you can basically use this inequality here, and then you can do the summation over the indicators and combine those things to be the expectation of u1. Okay, and the u's basically they have a finite first moment, right? So remember that u1 is x1 minus its first moment, and the expectation of magnitude u1 is basically this expectation here plus magnitude eta, and this is finite, and this is finite because by assumption we are assuming basically that our sequence of x's, the original sequence, has a finite first moment. Okay, and so basically we have here, this is a finite upper bound. Mission accomplished. Okay, so we proved that basically the condition that is there in the Kolmogorov strong law of large numbers, we proved that basically this condition is satisfied, and so yes, we can apply the Kolmogorov strong law of large numbers to the sequence, which is basically the y's containing each y with minus its first moment. Okay, so again, this may seem like misguided. Okay, what is going on? I mean, by the end of the day, we want to make something regarding the x's. So the trick now, or the challenging part now, is basically to start. So we have this, we have this idea. So, and again, now what is done is that this guy here now is shown to converge almost surely to 0 by the Kolmogorov strong law of large numbers. Okay, so now how can we, basically sneak the x's? Okay, the original objective. Okay, so here is the way to go. Can we say something about the y's? Can we say something about the y's without subtracting the first? Now, of course, I mean, you may, why actually we subtracted the first moment? Go back to the statement of the Kolmogorov strong law of large numbers. You will find that it is a statement regarding zero mean random variables. So that's the reason, we subtracted the first moments. So now the idea is, can we actually transfer this to the y's? Okay, well, we can do so if we show that, I mean, it's something you already from calculus, that if you have a sum of differences that converges, this does not necessarily mean that each is converging. Like, so you have this summation here, right? I to infinity 1 over I minus 1 over I plus 1. Okay. So basically this converges, right? Because it is, it's telescopic, and this will give you 1, right? But if you split this thing, okay, each one of the guys on its own is not converging because it's like the harmonic series. Okay, so this is very, very important. Like, I cannot, because I said that this is converging, I cannot basically say, okay, so this must be converging. It may not be the case. What I need to do is also to check that this sequence with the first moments of the y's is converging, is converging to 0. Okay, so basically this is this is what we want to do. We want to show that basically this is going to 0, and then we can transfer our almost sure convergence statement to basically the sum of the y's. Okay, so. So basically, we will basically show this by write down the required sum. Well, y is defined in terms of u, so write it in terms of u. Again, exploit the fact that the u's are identically distributed. So basically, having any u here will do the same in terms of expectations and probabilities. So I can just replace each one by u1, okay, and then here I will do the trick of basically rewriting the indicator as 1 minus the indicator with the complement condition. So indicator here, magnitude U1 is less than or equal to I will write this thing as 1 minus indicator that magnitude U1 is greater than I. And then basically we will replace, we will split this into two parts. So the first part is equal to 0 because the U's are 0 mean. Remember that, UI is equal to Xi minus expectation Xi. Okay, and so it's this 0 mean. So the sum of zeros will be 0. And then we have this basically term here. So take the magnitude of both sides. And if we can show that basically the magnitude here on the right, if it goes to 0 as k goes to infinity, then basically also the left hand side will go to 0 as k goes to infinity. Okay, and so so what we will do here is that we will apply the triangle inequality. Okay, so we have triangle inequality. So we will move the magnitude into the summation, and then we will move the magnitude from outside the expectation to inside the expectation. So actually, it's the triangle inequality like applied twice, and then we have this thing here. Okay, we have this thing here, and basically. What is this thing? So it's it is basically the claim is that actually it goes to 0. It's by one of the theorems that you learned in the tutorial session. Okay, that basically this will go to. So the idea is that you can use the dominated convergence theorem to show that limit I tends to infinity, expectation magnitude U1, indicator U1 greater than I. It's done here. I is equal to 0. So remember the Cesaro basically limit theorem is that if you have a sequence going to 0 or going to any limit, but now it's 0, then like the average here. So if you take basically j from 1 to I, aj, and then you divide by I, then this also will go to 0. Okay, so basically this is what we will do here. So this is again you have a summation from I to 1 to k and divide by k. Since this one again you can show by the dominated convergence theorem that it will go to 0, then this one will also go to 0. And now we finish this part. So yes. This part will go to 0, and so now we have a statement of convergence regarding the y's themselves. Very close to the end. Okay, so now the last thing is basically to go to the u's. Okay, so it's so again it's these are like advanced theorems are proved like this. I mean there is no like sort of a straightforward proof or something. You need like to do all these tricks that apparently will like complicate things. So rather than like dealing directly with the x's, then you deal with the y's. But now you need to go back, and the summation of the u's is the summation of the y's plus basically the summation of the difference between the u's and y's. Now we know that this guy goes to 0 almost surely by basically the argument on the previous two slides. And if we show that this goes to 0 almost surely, we are done. We are done, right? So we know that basically almost sure convergence. If you have something converging to 0 almost surely, something else going converging to 0 almost surely, then the sum will also converge to 0. Okay. So the last part here in the proof, basically, which will show that this goes to 0, and hence the x's will, basically, if this goes to 0, then for the x's they will converge almost surely to their first moment, which is assumed to be finite. The last thing is basically to show that this converges to 0 almost surely. And the idea is to use this definition for almost sure convergence, and its union I from m to infinity, magnitude ui minus yi greater than epsilon, and we have a union, and this is typical. I mean, in a couple of examples, we have seen that in some cases, it's not in all cases, But in some cases, basically the way to go is to start from this probability and to apply the union bound. Okay, and this will work again. This trick will work if after applying the union bound you get a 0, and so you say that this limit is 0. Okay, so if after the union bound you don't get a 0, then this trick is not working. But here you will try your luck. You say, okay, upper bound by the union bound. Then you have the summation that basically this difference is greater than epsilon, which is definitely greater than or equal to if the two guys are not equal, right? So here we are saying that the distance between ui and yi is greater than some positive number epsilon. So this probability is definitely upper bounded by the probability that ui is not equal to yi. But what is basically this event? So what is this event? Okay, so this event here, that basically we have that by definition yi is equal to ui, indicator the magnitude ui is less than or equal to I. So basically, when is yi not equal to ui? So yi is not equal to ui if basically this condition, if the indicator is not 1, and the indicator is not 1 if basically, so indicator is not 1 if the magnitude of ui is greater than I. Okay, and so basically this is equal to that, and so I claim that basically this limit will go to 0 because actually this summation, if you start this summation from 1, you will get a finite number. What? Who say that actually when you start this summation from 1 you get a finite number? Well, remember, this was the homework problem, an old homework problem, that basically the first moment of a non-negative random variable is upper bounded by these two quantities. So if the first moment is a finite number, then a summation that looks like this for any positive eta will be finite. And so what we have here is the special case when eta is equal to 1. So remember, there was this problem, I think it was like the very last problem in homework 5 or something like this. So it is basically an upper and lower bound on the first moment. And here is like one application, and it's very useful. Basically, it is what will finish off the proof for the strong law of large numbers. So we are dealing with the x's. They have a finite first moment. The u's have a finite first moment and a finite absolute first moment. And so basically this summation here is actually finite for every eta. And so it's finite for eta equals 1. And this is exactly what we have here, which means that now if we start our summation from m to infinity and take the limit as m goes to infinity, then the limit is equal to 0. So basically, this converges almost surely to 0. This converges almost surely to 0. The sum converges almost surely to 0. Remember that ui is xi minus mu. Then basically 1 over k summation I from 1 to k xi will converge almost surely to mu. So this is basically the masterpiece that is called the strong law of large numbers. And the final thing here, it's something that I left from the first slide. I mean, so it's basically 2 minutes. Basically, I want this thing here. I built a problem in the next homework based on it. So it is something that is useful to keep in mind. Almost sure convergence, again, it's not very much related to convergence in the earth mean, and it's not so much related to convergence of moments. So in the previous lecture, like you can have like a sequence converging almost surely to 0, while basically the sequence of first moments is converging to 1. So this is something that is, it can happen. Okay, but sometimes you can establish relations and you can make statements regarding convergence of expectations or moments if you have almost sure convergence. So this is one theorem of them, very useful, and keep it in mind. So here is the statement of the theorem. It is also called dominated convergence theorem. Dominated convergence theorem has like several versions. and this is one of them. So if you have a sequence Xn that converges almost surely to X. Now suppose that you have the following. Suppose that you have the magnitude of X of n is upper bounded by random variable y for every n. Okay, so suppose that there exists some random variable y such that magnitude xn is less than or equal to y for every n. Of course, y can be a degenerate random variable that is a constant. So perhaps, every random variable is less than or equal to 1. Or generally, it can be any random variable. Now, so if this is true, and basically this random variable, it has a finite first moment. So we need basically this, these three things. We need Xn converging almost surely to X. Now this alone, does not tell you about the convergence of expectations, for example. But now we have more. What we have is that for every n, magnitude Xn is upper bounded by y, and expectation of y is a finite number. Then in that case, if you take the expectation, if you have the sequence of the first moments of Xn, expectation Xn, then the limit as n goes to infinity of this expectation is expectation of X. Okay, so again, it may look to you like it should happen. Again, it's very tempting to think that if this is true, then this should be true. No. Okay, and again, like the example in the previous lecture, you can have convergence to 0 almost surely while the limit here is 1 or even infinity. But this may happen with extra conditions. And so the extra conditions basically that if magnitude x of n is upper bounded by y, and this is not enough, basically the expectation of y must be finite. Okay, if this is the case, then this statement is true, and you can use it in solving problems.